So the sun has joined the main sequence. Let's remind ourselves of what that means. That means we have a core in which hydrogen is fusing, generating helium. This is supporting the rest of the envelope by thermal and radiation pressure. And there's a theorem that the luminosity, surface temperature, profile, etc., is all determined essentially by the mass of the cloud, the ball of hydrogen you're forming. But there are also dependencies on the composition. What composition? It's hydrogen and helium. Yes, but there are those trace amounts of carbon, nitrogen, oxygen. They adjust delicately both the dynamics of nuclear reactions and of heat transfer. So metallicity makes a difference. In addition, the rate at which a star rotates can make a difference, the existence of a close binary partner, some effects in the atmosphere of the star, and when we're observing it, also unaccounted for effects in the interstellar medium can alter a star's appearance. These causes are why the main sequence is not an infinitesimally thin line, but rather a strip, because you have to account for differences in rates of rotation, composition, etc. And so, but other than that, the star settles down and sits there in equilibrium, and if it's a star with the mass of the sun, will sit there for about 10 billion years, during which time we saw things are not exactly static. There is some evolution going on. What is going on is that the core is contracting, and the main reason the core is contracting, you remember, is because of our old equation. P is N over V times K Boltzmann times T. When we take 4 protons and form an alpha particle out of them, and in the process eject 2 positrons that take 2 electrons out of the mix, we have gone from a total of 8 particles, 4 protons and 4 electrons, to a total of 3 particles, 1 alpha nucleus and 2 electrons. And the net result of this is that the number of particles is decreasing. If the core does not contract, then the pressure will decrease. Pressure can't decrease because it's holding up the external envelope. There's no real intuitive reason, a way I can think of to explain this, but the net result is that the compression and the resulting heating of the core more than compensate for the decrease in the concentration of hydrogen. The rate at which fusion is occurring increases, and then the core is now producing more luminosity, more energy. The need to push more energy through the envelope puffs the envelope out, and so the radius of the star slowly increases and its luminosity slowly increases. And since the rise in temperature of the outer envelope does not track the main sequence, the star is starting to turn away from the main sequence. If the temperature is not changing, it's moving vertically up the HR diagram. And this is where we pick up our story and where things start to be interesting. So we meet our sun at the ripe old age of about almost 11 billion years. It has grown somewhat, as we discussed. It's got a radius of about 1.6 solar radii. It's got a luminosity that's almost double what it started with. By now, it has been accumulating helium in the core to the extent that the inner 3%, not by volume, but by radius. So the first 0.03 of the solar radius is essentially a chunk of helium, or a ball of helium, and the helium just sits there. It's inert. It's not producing energy. Therefore, there's no temperature gradient. There's no flow of energy out of the helium. So there's no temperature gradient. It's all at the same temperature, which is the temperature of the hydrogen immediately adjacent to it. And outside this helium core, of course, is a shell of hydrogen in which fusion is occurring, and that's what's powering the star. And the rate of fusion in the shell exceeds the rate that was previously going on in the core, which is why the star is more luminous than it was. And over these 11 billion years or so, the envelope has slowly been expanding, and the core has slowly been growing as hydrogen fuses in the shell. More and more helium is being deposited into this inert core, which begins to grow. And this is a picture of the solar system at this point in time. Where we are in terms of the sun's main sequence and evolutionary track is that for the first 10.5 billion years of its existence, the sun sat very happily at this point, and it is now rising away from the main sequence. Its luminosity is increasing, and its temperature is starting to decrease slightly as the envelope puffs out. So the evolutionary track is turning somewhat to the right. what's the next thing that happens? Well, there is an issue here, and the issue is, we'll maybe have an optional clip where I'll do a calculation associated to this, but the core being isothermal means, again, PV is NKT. You need higher pressure in the center of the core than at the outside of the core because the center is supporting the mass, the weight of the outside against gravity. This means the center of the core has to be more dense than the outside of the core. Not too complicated a calculation from this shows you that if the core is too large a fraction of the star, it cannot support the weight of the outer layers, no matter what density you give it. And what this tells you is that as the core, in fact, the calculation, if you do it in detail, shows you that a core whose mass is more than 8% of the mass of the star cannot support the atmosphere outside it. When the mass of the inert helium core in the center of the sun exceeds 8% of the solar mass, and it will, remember that's about the mass of Jupiter, when it exceeds 8% of the solar mass, it can no longer sustain the weight of the atmosphere, and the core starts to collapse. Collapse rapidly. What is rapidly? Rapidly means on the gravitational scales. Tens of millions of years. That was this Kelvin-Helmholtz scale we talked about. So the core starts to collapse rapidly. This releases, of course, a great deal of Kelvin-Helmholtz gravitational potential energy. It also compresses the hydrogen-burning shell immediately outside the core because that falls in as the core collapses. This, in turn, increases the luminosity that hydrogen shell is putting out. That puffs out the star's atmosphere and cools it down, and the result is that the envelope has puffed up, its radius is larger, the external temperature decreases, so the star starts moving to the right along the HR diagram. This is what the solar system will look like with a larger, cooler sun. Notice the time, 700 million years have elapsed, and the sun is now a subgiant star. It is moving, it'll spend these 700 million years moving to the left and slightly heating up, moving to the right, so cooling down and slightly increasing in luminosity as the envelope puffs up. What's a subgiant star? Well, an example of a subgiant star is Procyon in Canis Minor. You can look up its data. That's a good example of a subgiant star. Notice the sun will only last about 700 million years as a subgiant, whereas it lasted 10 billion as a main sequence star. Subgiants are more rare, but because they are luminous, notice the sun will be more luminous at the end of its subgiant phase. We can see some of them. So we've left our core collapsing. What does that do? Well, once the core starts to collapse, then compression heats the shell, luminosity of the hydrogen fusion shell increases dramatically. This puffs up the envelope. As it puffs up, it cools down. It cools down to a temperature of a few thousand degrees, where negative hydrogen ion opacity again controls the opacity of the external atmosphere. So it's approaching that Hayashi temperature that we talked about. Because the external atmosphere is opaque, that means that instead of radiation transfer at the outer atmosphere, we have sort of deep convection cells over here. These dredge up to the surface the products of early fusion in the core, and we see a change in the spectrum of the star. What comes up? Well, trace amounts of carbon, nitrogen, and oxygen whose isotopic abundances have been slightly shifted by the CNO processes that have been going on, albeit at a small rate, in the interior of a star. In a bigger star, we'd see the CNO abundances that are adjusted by the action of the CNO cycle. Now, whenever a star puffs up this large, note the sun is acquiring a radius of 160 solar radii. It's doing it rather quickly, within about 600 million years. This quick puffing up is always accompanied by enhanced stellar wind and mass loss. Notice that the outer layers are now much farther from the center than they were, much less strongly gravitationally bound. So the sun at this point might lose as much as 28% of its mass in its red giant phase. The way this would look in the solar system is that poor Mercury will have completely been subsumed in the sun. Venus and Earth still exist, albeit temperatures there would be very hot. What's an example of a red giant that we know? Well, the star we call Aldebaran, and probably should call Aldebaran, is a red giant with 1.7 solar masses, so it's a slightly more massive than the Sun. Red giant with a luminosity about 500 times that of the Sun. And at the peak of its red giant phase, and we'll talk about that, the Sun will have a luminosity over 2,000 times the current solar luminosity. And so the Sun is puffing up, cooling down, and this goes on, and the core is collapsing. Now, neither the puffing up and cooling down can go on forever, nor for that matter can the core collapsing. So something's going to stop the core collapse. And remember that thermodynamic pressure is not able to do this because of this Schoenberg-Chandrasekhar limit that we talked about. There is no way for the core to support the external atmosphere unless something happens that we haven't taken into account yet. Before we go there, let's remind ourselves where we are on the HR diagram. We have finished the subgiant phase, and we are now climbing the red giant phase. And this phase is the phase that will last for the next 600 million years or so. And the Sun becomes more and more bright, more and more luminous at a pretty constant temperature, determined, as I said, by H- ionization. And then what? Well, first of all, the core cannot continue to collapse. Its collapse is stopped by a quantum effect called electron degeneracy pressure. We'll meet this effect again, and while we haven't done much quantum mechanics, we can explain some of it. Electron degeneracy is the result of the Pauli exclusion principle, which, remember, tells you that only one electron, or two if you account for spin states, can occupy a given state, and there is a finite number of electron states up to a given energy in any volume of space. This electron degeneracy, if you want, is the reason why when I clap my hands, they don't go through each other. All the low-lying states in this region of space are occupied. All of these electrons would have to be excited to higher energy states. The neat thing about this is it has nothing to do with temperature. Even if you have zero temperature, the electrons are all at the lowest possible states. If you try to squeeze too many of them into too small a volume, some of them have to reach excited states even at zero temperature. So what this does is it produces a temperature-independent contribution to the pressure. When you try to squeeze a system with electrons in it too tight, one of the things you're doing is you're squeezing some electrons into higher energy states. In normal systems, this is not, in normal gases, this is an irrelevant contribution. Even at the center of the Sun, you can make a calculation that it's less than a fraction of a percent of the total pressure at the center of the Sun. But when this degenerate helium core, when this helium core collapses, its density becomes so high that in fact electron degeneracy pressure is what ends up supporting the Sun's atmosphere. And what is going on is that the degeneracy pressure, as I said, is temperature independent, but it's very strongly dependent on density. It increases as the density to the 5/3 power. The constant Ke is slightly dependent on the details of the model, and for the parameters relevant to the Sun, I gave it here. If you plug it in, as I said, you'd find that the Sun is highly non-degenerate today, but that the helium core will become degenerate, and this is what will cease its collapse. The important thing about degenerate matter is that its pressure is independent of temperature. If you heat a gas, it will expand because when T goes up, P goes up. When you heat a degenerate gas, it will not expand because P is completely independent of T until thermal pressure grows enough to overtake degeneracy pressure. So this will stop the core's collapse. It will stop when it reaches degeneracy. What does that do to the outside of the Sun? We'll see in the next clip.